Today we're going to look at maximum and minimum values of a function. Maximum and minimum values of a function. Okay? And as you can see, I've got some graph paper here set up. We're going to do a bit of graphing, so if you have graph paper handy, I'd recommend using it if you're going to take some notes. Okay, so before we get to examples on the graphs, let's look at some definitions of maximum and minimum values. And let's start with what are called absolute. Absolute or global is another word that we use in place of absolute. So absolute or global, maximum and minimum. Okay? So this is the absolute case or the global case. Let's talk about this concept. And so what we say is that an absolute maximum or minimum basically relates to the highest point on the graph or the lowest point on the graph of a function. Okay? Now you're not always guaranteed to have either one. So we'll come back and look at some examples shortly. But mathematically, the way we would describe this is we'd say, okay, some output of a function f. So one way we could say that is f of c. So this is the output of function f for some number c, some specific number c. F of c is the absolute maximum value of f. Now be careful, don't read this as the absolute value of f. It's the absolute maximum value. This is a definition. So this output is called the absolute maximum value of the function if that output, f of c, is bigger than or equal to all other outputs of the f function. So bigger than or equal to every f of x. In other words, for every x in the domain of f. Every x in the domain of f. So if this particular output is bigger than or equal to all the other outputs of this function, then we call this output f of c the absolute maximum value or the global maximum value of the function. Okay? Now you can imagine that with a couple small changes, we can make this the definition of absolute minimum value. So I'll replace maximum with the word minimum in red here. So rather than write out an entire new definition that's almost exactly the same as this, I'll just write the corresponding changes in red. So now we say f of c is the absolute minimum value of f if now instead of this f of c is greater than or equal to f of x, we say f of c is less than or equal to f of x for every x in the domain. Okay? So now the output is smaller than or equal to all the other outputs. And that's mathematically the way we describe the absolute maximum and minimum. Let's look at one more type of maximum and minimum, and then we'll come to our graph and sort of illustrate some tricky little nuances about these definitions. The absolute case is pretty straightforward, but the next one can be a bit tricky, so we need to spend a little bit of time on this. Okay, so the next definition, if you're not talking absolute maximum and minimum, you can discuss what's called the relative maximum. Relative, or if absolute is global, relative is called local. So these could be called local also. So relative maximum and minimum. And so now we say that f of c, this output of this function, f of c is, and right away there's a difference. A function can only have one absolute maximum value. Okay? That one y value that's greater than or equal to every other y value. Now, it may not have any. There may not be an absolute maximum value. But if there is, there's only one. Relative maximum and minimum, you could have more than one of each. Okay? You may not have either of either. Sorry about that. But you could have more than one also. So now we don't say f of c is the relative maximum value. We say f of c is a relative maximum value of f. And again, this is a definition of relative maximum value. So f of c is a relative maximum value of f if, similarly to the last definition, if f of c is greater than or equal to f of x. And what changes here is what follows this. Which x values does this need to be true? If it were true for every x value, then this would simply be the definition of the absolute maximum value. But instead, when we're talking local, we're talking about x values that are close to this input c, right? C is an x value. So now we're looking at x values that are close to c. So if f of c is greater than or equal to f of x when x is what we call near c, meaning sufficiently close. If you get close enough to c, and from both sides, that's important. You have to get close to c from both sides. The outputs of all those x values that are close to c are smaller than or equal to the output at c, okay? And so let's go ahead and polish off this definition where we change it to now the relative minimum value. Again, you could also call it local maximum value or local minimum value. But now I can make this the definition of a relative minimum value by saying that f of c is less than or equal to f of x whenever x is near c. Or you could say for every x near c. Maybe you like that language better. Okay? So now let's come to our graph. We'll draw up an example and we'll discuss the maximum and minimum properties of a particular function, okay? So let's say the instructions for this problem are to identify all max and min values of f and the x values at which they occur. Okay? Identify all the maximum and min values of f and the x values at which they occur. Now, that's not terribly specific. I could throw in the words absolute, relative, global, local, whatever, and it'd be more specific. But here we're just going to do it all. We're just going to practice with it all. So I'm going to construct a graph here, and we'll kind of do this discussion now. So let's say that our graph, this is the graph of f, by the way. Let's say that our graph has a vertical asymptote here at 1. So we have vertical asymptote here at 1, and from there it's coming up and sort of hits this point right here. So it's getting infinitely close to our asymptote there. It comes up and it hits this point, and it comes back down. Let's see here. Comes back down to an open circle at the ordered pair 3, 1. Okay, so it hits this peak here at 2, 4, comes down, hits an open circle at 3, 1. And then it picks back up with a closed circle at 3, 2. Okay? And from there, it drops down to 4, 0, comes back up to 5, 2, and at 5, 2, it's got a closed circle again. And then after that point, picks back up at 6, 3 with an open circle, and comes up to the point 7, 5 with a straight line at a closed circle. Okay, so pause the video, copy this down if you're taking notes. But let's discuss the maximum and minimum values of this function, okay? So when we're looking at this function, let's first categorize. Let's say we're looking for absolute max, okay? Let's look at that first. Absolute max. In other words, is there any y value on this graph that is bigger than or equal to every other y value on the graph? And so you're literally scanning for the highest y value, and that seems to be 5. Nowhere on the graph do we rise above the y value of 5. So 5 is the absolute max value at, and in this case, it occurs at the x value of 7. Okay? So there's our absolute maximum. Let's discuss, and here I don't want to mess that up. Let's not mark on that any more than we need to. Let's talk about absolute minimum. So in this case, is there any y value that's lower than, smaller than, or equal to every other y value on the graph? And so a lot of students will look and they'll say, well, yeah, right here the graph bottoms out at the order pair 4, 0. Okay? But the problem is, over here on this part of our graph, we have an arrow that goes down and doesn't stop. It keeps getting infinitely close to this asymptote. So it's never going to reach a bottom. We're never going to have a lowest y value in this particular graph. So there is none. There is no absolute minimum. Okay? All right, let's talk about relative. So absolute's pretty easy, but let's talk about relative now. So let's get rid of this. Actually, let me mention one thing here real quick. If for example, if this circle here was open, don't change your notes, just maybe make a little side note if you need to. But if this point at 7, 5 was an open circle, now that's an interesting question. What would the absolute maximum value be? What would the highest y value be on this graph? Well, would it be 4.5? Would that be the highest y value? It hits 4.5, right? But it clearly hits points higher than 4.5. So would it be 4.75? No, it hits points higher than that. In fact, this open circle indicates that we're getting infinitely close to the y value of 5, but we never reach it. So if we had an open circle here, this particular function would not have an absolute maximum either. But for a completely different reason, that it doesn't have an absolute minimum. This arrow, this graph never stops moving in the negative direction, so it doesn't have an absolute minimum. It certainly stops moving in the positive direction, but there's no particular value where it stops, right? We have a boundary point here where y is 5, but it doesn't reach that boundary point. It just gets infinitely close. So that's kind of an interesting little side note there that you may want to write down. Okay, let's resume our discussion though, and let's pick up with the relative. Let's do relative max first. So relative max is a y value that's higher than all the other y values for points that are close from the left and the right. Okay, so for example, this point right here at 2, 4, if you look at that point, in the c value that we're talking about, if you remember the definition, the c value we're talking about in this case is 2. So we're looking at x values close to 2 from both sides, And if you trace up and look at the outputs of those, all the x values within that range of 2, all of those have y values that live here. So what we call this maybe a neighborhood of 2. All the y values in this neighborhood are less than or equal to 4. So in this case, 4 is a relative max. 4 is a relative maximum value. That's key to say it's a value, by the way, because it's a y value. 4 is a relative maximum value, and it occurs at x equals 2. Right? This point is higher than every other point in the neighborhood on both sides of 2. No matter how small you make this, that point will be the highest. All right, are there any other relative maximums? Well, what about, what other local high points do we have? What about this point right here at 3, 2? All right, so we do the same analysis. We look at both sides of 3 and we ask ourselves, okay, if we look at all the outputs here, when we're really close to 3, we get these y values on this half of 3, and we get these y values on this half of 3. And this point at 3, 2 is the highest point, no matter how small you make this neighborhood around 3. So 3 is also a relative maximum value, and that occurs at 2 is the y value here. Sorry, I was looking at that wrong. 2 is a relative maximum value at x equals 3. Okay? All right, so here we go, right? Now you're asking yourself, well, now this point at 5, 2, that's got to be a relative maximum also, right? Well, it's a bit tricky because now if we look on both sides of 5, right, no matter how small I make this, I can certainly get outputs on the left side of 5. I get all of these y values right here on the left side of 5. But if I look at the right side of 5, this graph doesn't have any outputs, no matter how small I make it. And that's why we say near 5, because we can make this as small as we need to. But no matter how small I shrink this neighborhood around 5, there are not going to be any y values on the right side of 5. So we can't say that this y value is higher than every other y value on both sides of 5 because there are no y values on the right side of 5. Now, you probably need to pause the video and write some notes to yourself about this because that's one of the trickier aspects of relative max and mins. Okay? So we do not have a relative maximum value of 2 at x equals 5 here. Okay? Now, let's continue our discussion. And the next obvious place we need to look is probably at this point at 7, 5, right? And you can see that if we look at both sides of 7, we have the same problem where no matter how close we get to 7 on the right, we're not going to get outputs over there. So we have no relative maximum value there either. Okay? Now let's talk about relative minimum. What are points that are the lowest in their neighborhoods? Well, the first candidate we have, you can't use this arrow, right? Because there is no lowest point. It keeps going down, so we can't use that. Now, the next point that seems to be the lowest point is right here at 4, 0. And luckily, this function is defined on both sides of 4, and no matter how small we make that neighborhood around 4, this point at 4, 0 is lower than all those y values within that neighborhood around 4. So what we have is, we have 0, that's the y value here. 0 is a relative minimum value at x equals 4. Okay? So this should start making sense now. We're doing lots of examples here. Now the next candidate for the lowest point in his neighborhood might be right here where this open circle is. But as we discussed before, there is no lowest point right here, even though the graph terminates. It doesn't keep going with an arrow, but because that's an open circle, that indicates that our graph keeps getting infinitely close to that y value of 3, but it just doesn't quite get there. Okay? So there is no relative minimum at this open circle. And so here we have a full discussion of the maxes and mins of this particular function f, and with regard to absolute max and min and relative max and min.